In this lesson, we're going to predict the changing direction of a reaction. So up until now, all the calculations that we have done have been once equilibrium has been reached. So what we're going to look at today is what if we haven't reached equilibrium yet? How are we going to predict the direction that the reaction is going to move in order to achieve equilibrium? So do more products need to be made? Is it the forward reaction that's going to occur? Or do we need more reactants to get to equilibrium, in which case the reverse reaction would be happening? So we're going to use the reaction quotient, which is Q. So up until now we used the equilibrium constant K, EQ. And so now we're going to look at what is called the reaction quotient, QEQ. And then we are going to compare that to the equilibrium constant KEQ. And we're going to use that to determine whether the reaction is going to move in the forward direction or the reverse direction to reach equilibrium. So the reaction quotient is calculated the exact same way as the equilibrium expression is. So when we have a particular reaction, we have the products over the reactants, and the coefficients that we have in our balanced equation become the exponents in this. So the expression is the exact same for KEQ and QEQ. The difference is that the concentrations used have to be at equilibrium in KEQ. So for the equilibrium constant, the concentrations used, so these amounts, are equilibrium concentrations. In QEQ, our reaction may or may not be at equilibrium. So QEQ, we're going to use that to determine which way the reaction needs to move in order to reach equilibrium. So these will make a lot more sense once we look at an actual example, but if the value that we get for QEQ is the same as the equilibrium constant, then the reaction is at equilibrium. So this one's probably fairly easy to understand here, that if my value for QEQ, when I plug in my the concentrations of products and reactants, is the exact same as KEQ, then that means that the concentrations used are equilibrium concentrations. So if QEQ is lower, then what's going to happen is the reaction is going to move to the right to reach equilibrium. And if KEQ is larger, then the reaction is going to move to the left. So if we think about the fact that both QEQ and KEQ are products over reactants, so if QEQ is smaller, so looking at this one first, then what we need to be, that means that we need the top number to get larger. So if we have a smaller number than where we need to end up, then in order for our number to get larger, we're going to need more products. So this one is going to move towards the right. So products are going to be made here. So we're going to have products and reactants happening. So remember, both the forward and the reverse reactions are always happening. What we're really looking at here is the overall change. So although we will have both products and reactants being made, until we reach equilibrium, we are going to have more products made than reactants. So we're going to say that this reaction needs to shift to the right. More products need to get made to get to equilibrium. If QEQ is larger, then in order for us to reach KEQ, I'm going to need more reactants. I'm going to need the number on the bottom to get larger and the number on top to get smaller, so that we can lower the number to get down to KEQ. So once again, once we look at examples with actual numbers, this will make more sense. So we have a particular temperature. Remember, our KEQ values are always only valid for a particular temperature. So at a certain temperature, the equilibrium constant is 55, And the reaction vessel has a mixture with the following concentrations: 0.85 moles per liter of SO3, 1.2 moles per liter of NO, 1.5 moles per liter of SO2, and 2 moles per liter of NO2. So is that at equilibrium? And if not, which way is the reaction going to proceed to reach equilibrium? Is it going to move in the forward direction or the reverse? Okay, so here are all our concentrations and the equilibrium constant from before, as well as our equation, which is balanced. So our QEQ, once again, it's the same as KEQ in terms of setting it up. So I have my products first, so SO2 and NO2. Now because we have 1 and 1, our exponents are 1, which we don't need to write in, and over SO3 and NO. So SO2 is 1.5, NO2 is 2.0, SO3 is 0.85, and NO is 1.2. So we're going to calculate this quickly. And our KEQ value is 2.94. So my KEQ, which is given to me in the question, is equal to 55. So when I do products over reactants, my answer needs to be 55. Right now, it's 2.94. So because our expression is a fraction, we have products over reactants, what we can always do is just put everything over 1, and then that turns those into fractions as well. So in order to reach equilibrium, we need to get from 2.94 to 55, which means the top number needs to increase. And what is on the top is the products. So what that means is some of the reactants need to become products. So that will reduce the bottom number in the fraction. It will increase the top number so that we can get to a ratio of 55:1 between them. So if we put everything over 1, what we can see is the bottom is the same, and so the top number needs to increase to get to equilibrium. So KEQ is my equilibrium amount, and what's on top is products. So if QEQ is smaller, then we need more products, which means that this is going to shift to the right, or it's going to proceed in the forward direction, or more products are going to be made, or it's product favored. So we have multiple ways of saying the same thing here. Okay, so what about if we actually make some changes to our system? So changing concentration or temperature or pressure or volume. What happens in that case? How does that shift equilibrium? So this is called Le Chatelier's principle, and it is just letting us know that if a system is at equilibrium, but there is some sort of external stress that is applied, then equilibrium is going to shift to minimize that stress. So equilibrium is just a balance between the forward and the reverse reactions. We already saw that if we have a KEQ, that is only valid at a certain temperature. So as we change the temperature, the equilibrium constant is different, which means the concentrations of products and reactants are going to need to change to get to that value. So that will shift it. But also, if we add or remove any reactants or products, that will also cause some changes, and so will changing pressure or volume. So any changes that can be made are referred to as stress. And then the response in a system is called Le Chatelier's principle. So the three stresses, as I mentioned, can be changing the concentration of any of the reactants or products, changing the temperature, or changing the pressure or volume. And those are tied to one another. So if I reduce the volume of something, so if I start with a certain volume And in that container, I press down a lid so that the volume, is smaller. So let's say I have, each of these represents 1 mole. So if I have 5 moles in there, then those 5 moles are going to have to come a lot closer together with a smaller space. So if I'm pressing down on that lid to reduce the volume, I am increasing the pressure. So I'm pushing down. That's forcing the molecules to be closer to one another. So they have less space. They're going to be bumping into each other a lot more often. So a reduction in volume is similar to an increase in pressure as well. Okay, so when we change the concentration, so that could be done by an increase or decrease, and that can be of any of the reactants or products. So if we remove a reactant, what we are going to do is shift to the left, which means towards the reactants, to replace whatever is lost. So anytime we remove, we are always going to move to that side to replace. Similarly, if we remove product, then we are going to want to replace product. So if we think about the KEQ, the equilibrium constant, which is products over reactants, if I take away some of the reactant, that is going to change the ratio between my products and my reactants when I plug in my concentrations, and I won't be at KEQ anymore. So in order to fix that, some of my products need to become reactants. So what that will do is, it will, oh goodness, that was not placed in a good place. When we reduce some of the products, so when my products become reactants, it means that this number will get a little bit lower, this will get a little bit higher, so we can get back to what the original ratio was. So we're already starting by reducing this number. So if some product becomes reactant, now we can bump this number up a little bit and this one down until we get to that point where our KEQ is the same again. So similarly, if we remove product, so let's just rewrite this. And so if we remove product, now our number down here is quite a bit larger compared to what we had before. And so we're going to replace some of that product. So our reactant will shift and become product. So when we remove, whether it's a reactant or a product, we're going to replace whichever one we removed. So removing reactants, we replace reactants. We're shifting to the left. Removing products, we want to replace products. So we shift to the right. So this is just what, this is now adding. So the reverse of that happens when we add. When we add more reactant, this number is now going to increase. And so what I want to do is some of that is going to become product to lower this number back down a little bit, increase this one to get to that same ratio that we had. So adding reactants, we are going to shift away from them. So we want to use some of those up and make some products. And if we add products, then we're going to want to remove part of what was added by making reactants. So when we remove, we shift towards the side where we removed from to replace. When we add, we shift away from the side that was added to remove part of what was added, to counteract that change. So here we have the Haber process, nitrogen and hydrogen combining to make ammonia. So if we were to add in more ammonia, so whatever I add in, if I'm adding in this case, reactant, so that's down here, that is going to increase that number on the bottom. And so I'm going to want to replace some product. So I want some of that new reactant to become product to get back to equilibrium. So adding more ammonia is going to shift away from that side. So that's going to Oh, sorry, ammonia, not nitrogen. This is going well. Okay, so if I add in ammonia, I'm going to shift away. So this part was wrong. So what I'm adding more of is that. So what I want to do is some of the product that I add is going to become reactant. Oh, look, we already did this one. So add more nitrogen, we're going to shift away from it. We're going to shift to the right. And if we remove hydrogen, so when we remove something, what we want to do is replace it. So that is going to shift to the left towards the reactants to replace the hydrogen. Okay, temperature works similar to concentration. And we talked about endothermic and exothermic reactions in enthalpy, and we wrote our heat as either a reactant or product. So if our delta H, if our enthalpy change is negative, it's an exothermic reaction, and so heat is one of the products. Heat is produced. So just like with concentration, we are going to look at heat as a product. So we can either add or remove heat, which in this case is a product. So if I increase the temperature, it means that I am adding in more of a product. And anytime I add more of a product, I shift away from. So in an exothermic reaction, because heat is a product, if I increase the temperature, then this is going to shift towards the left to counteract that increase in heat. If I lower the temperature, then it's the same as taking away one of the products, and so to counteract that, I want to replace some of that heat. So in that case, it's going to shift towards the right. And then the reverse happens in an endothermic reaction, and that is because this time our heat is a reactant. So if I increase the temperature, so if I'm adding in more heat, then I'm going to shift away from. So I've just realized as I'm doing this, I don't know what I did in the last one, but this looks like a decrease. So what I'm doing is pointing towards this because I'm adding it in, and when I point away from it, that's because I'm removing it. So what did we do over here? Yeah, so adding it in and then taking it away. Okay, so if we lower the temperature, then that's the same as taking heat away. And if I remove something, then I want to replace it. So that is going to shift to the left to replace heat that was removed. So over here we have A plus B becoming 2C. Delta H is positive 40. So positive means that it is an endothermic reaction, which means it's going to show up on this side of the equation, on the left side. So if we remove heat, if we are taking it away, then we want to replace. So that's going to shift to the left. And if we are adding it in, then we want to move away from to counteract. So some of the reactant would become product when we're adding in reactant. So that's going to shift to the right. Okay, last one, when we have a change in pressure or volume. So liquids and solids aren't affected by changes in pressure or volume because those particles are always hanging out near each other at the bottom of the container, affected by gravity. But once the intermolecular forces holding molecules together is overcome and something becomes a gas, then they can float away from each other and they fill a container. And so here we can actually push molecules closer to one another, or we can increase the space and allow them to move further away. So gases are going to be impacted by pressure and volume changes. So a decrease in volume or an increase in pressure is always going to favor the side of the equation that has the least amount of molecules. So if I have a certain volume to start with, and I have 5 different molecules in there, and I decrease my volume, so I'm pushing down on the top, so I'm increasing pressure, decreasing the volume. So now these 5 particles are a lot closer. So if this reaction can move to an opposite side, so if some of these can combine and react to make 1 molecule, then I would have less than 5 molecules in there. And so that's what's going to happen with pressure and volume changes, is the less space there is, the more pressure there is, the side of the equation with less molecules is going to be favored. And if I do the reverse, if I increase the space that I have, or I decrease the pressure, so same idea there, then now what can happen is if these 2 were to combine and make 3 molecules in the reaction, then that is going to be favored. So now I have enough space in there to have more molecules. So an increase in volume or a decrease in pressure is going to favor the side with more molecules. So a couple things, if we have an equal number of gas molecules on both sides, then there's actually no impact to this. So once again, only gas molecules and equal numbers of gas molecules, then there's no change. And then the other thing is if we add an inert gas that is at constant volume, there's no impact on equilibrium. So an inert gas is something that is not going to react with anything. So one of the noble gases, if we were to add that in, that would make no impact. So if I increase the pressure and decrease the volume, what is going to happen here? So increasing pressure, decreasing volume. So if I have a certain starting point and I press down on the top to make less space, what's going to happen? So what I want to do is look over here. I have 2 and 1, so 3 total molecules of reactants, and on this side I have 2. So if we have less space, we are going to favor the side that has less molecules. So this is going to favor the right side or the product. So it's going to shift to the right to counteract the stress. Over here, I have 1 and 1 for a total of 2. And I also have 2 on this side. So there's no difference. It doesn't matter whether it goes in the forward or reverse direction. We're not going to change the number of molecules there are. So here, there's going to be no change to equilibrium. And over here, so here I have, this is a solid, so it doesn't count. This is a solid, it doesn't count. And this has 1 gas molecule on this side. So this has no gas molecules, 1 gas molecule. So if we are going to make our space smaller, we want to shift away. We would move towards the side that has no gas molecules. So this would shift to the left.